Newton's method is an algorithm for approximating zeros to functions, places where they cross the x-axis. So I'm going to start this lesson with a concrete example and explain the process while I'm doing it, and then we'll automate it using your calculator as much as possible. So here's what I want to do. I have a function, in this case it's a polynomial, f of x equals x cubed plus x plus 1. It has one real zero, and I want to approximate that using Newton's method. So if you see on the graph, I've graphed it, taken the opportunity graph. The point that I want is somewhere between -1/2 and -1. Now, with Newton's method, the first thing you do is supply a guess. To make life easier, my guess is going to be -1. So my guess, I'll call it GUESS, is x sub 0 equals -1. Now, after that, you locate -1 on the graph, and then you find its point on the function itself. So if you look, -1 is the point on the graph that is directly beneath x equals -1. Now what I'm going to do is calculate and graph the tangent line that goes through this point -1, -1. So compute the tangent line at x equal to -1. All right, well that's not so bad. The derivative, f prime of x equals 3x squared plus 1. So f prime of -1 equals 3 times -1 squared plus 1, and that's equal to 4. So my tangent line I have a point, -1, -1, and I have a slope. So my tangent line is y minus -1 equals 4 times x minus -1. Or a little more simplistically, y plus 1 equals 4 times x plus 1. And should you want to go through the effort of writing it in slope-intercept form, I'll solve for y. Y equals 4x. I would have 4x plus 4, but I'm going to subtract off this 1, so I have 4x plus 3. So in the picture that we're looking at here, this line here is y equals 4x plus 3. What I'm interested in is where it strikes the x-axis. If you'll notice, where it strikes the x-axis is closer to the 0 than the original guess. My original guess was this far away. If you look now, this new guess is closer to the answer. So this right here, the place where it strikes, I'm going to call x sub 1. Well, where is x sub 1? X sub 1 is the y-intercept, the x-intercept of this tangent line. So x1 is the x-intercept. I'm being a little clumsy. Usually when I talk about an intercept, I'm talking about a point, but I'm going to lay off a little bit on that and just use x1 as the x-intercept. That means that x1 solves this when y is equal to 0. So I'll replace y equal to 0, and I'll get 4x1 plus 3. And then I'll solve for x1. I'll get -3/4 equals x1. All right, now what we do, I keep showing many of the same pictures over and over and over again. Let me go to an even more zoomed in picture of this. Right here is x1 equals negative 3/4. And now I'm going to play the same exact game I did before. I'm going to go down to the graph, find this point on the graph below negative 3/4. That'll be negative 3/4, comma, something. And then I'm going to get a tangent line through there again. So let's calculate that point first of all. F of negative 3/4 equals negative 3/4 cubed plus negative 3/4 plus 1. That equals negative 27 over 64 minus 3/4 plus 1. Let me get it all over 64. And you'll find that this equals negative 11 over 64. So this point here is negative 11 over 64. Now, in the next step, I'm just identifying the point much more closely. This here is negative 3/4. X1 equals negative 3/4. A million different views. And this is negative 3/4, comma, negative 11 over 64. My next guess then, I'm going to draw a tangent line. I'm going to go down here. I'm going to draw a new tangent line through this point that's going to strike the x-axis even closer. And that'll be up here. That'll be my x2. Well, how do we do that? Well, I calculate a new tangent line for x equals negative 3/4. So we already had f prime of x was 3x squared plus 1. So f prime of negative 3/4 equals 3 times negative 3/4 squared plus 1, which equals, this will be 9 over 16. With the 3 there will be 27 over 16 plus 1. And that will equal 43 over 16. So there's the slope of my tangent line. This tangent line right here. Y equals 43 over 16 x. Now the x value was negative 3/4, so I'll have x plus 3/4. The y value, let me erase that y, not quite, that's y plus 11 over 64. So that there is the tangent line. I'm not going to bother solving for y. It's not really necessary. Now if I want x2 then, that's the x-intercept for this tangent line. So that means y equals 0. So x2 is the x-int for this tangent line. Y plus 11 over 64 equals 43 over 64 times x plus 3/4. And then if that's the x-intercept, that means that y is 0 when that x2 is in. So I'll have 11 over 64 equals 43 over, I think I made a mistake here. I did. That was a 16 down there. I'll put my x2 in here and I'll try to solve for x2. First thing I'll do is multiply by 16 and I'll get 11 over 4 equals 43 times x plus 3/4. I'll divide by 43, so I'll get 11 over 172 equals x plus 3/4. I'll subtract 3/4 from both sides. And I'm losing my 2's on the x's. And we end up with, if I get this to a common denominator, 4 goes into this 43 times, I already know that. 43 times 3 is negative 129. So this is going to be negative 118 over 172 equals x2. I don't mind simplifying it. Negative 59 over 86 equals x2. And you can see I've tried this equals negative 59 over 86. And then, of course, what you're going to do at x2 is draw another tangent line, and it's going to cross the x-axis even closer. And you keep doing this over and over and over until you get the accuracy you require. Now, I have no intention of having you do this by hand. I just wanted you to see how it sets up. Let me show you in general how the formula shapes up and how we can use the calculator to automate most of this for us. So, the general setup. Basically, you're going to be honing in on some sort of a zero of a function. Let's say this is my function f of x. And this is the point that you're trying to estimate. Let me take out some things here. Let's say this is the guy you're trying to estimate here. That's the answer to the problem, let's say. You'll pick some sort of a guess, call it, say, x sub 0. That'll be your guess. And then what you'll do is you'll go up to the x-axis and find where it intersects, up to the graph and find out where it intersects the graph. And then draw a tangent line from that point and allow it to continue and strike the x-axis. That's the tangent line there. Now the new place where it strikes the x-axis we'll call x1. And you can see x1 should be closer than x0 was. And then you'll just repeat the process over and over again. So this point here, the tangent point, goes by coordinates x sub 0, f of x sub 0. If I want the equation of this tangent line, well, that's easy enough. The slope is f prime. So the tangent line equation you're going to have the slope will be f prime of x sub 0. The point is x0 f of x0. And then x1 is the solution when y equals 0. x1, of course, being your next guess. So let me throw that in here. 0 minus f of x0 equals f prime of x0 times x1 minus x0. Obviously, there's going to be an issue if f prime of x0 is equal to 0, so we're blatantly going to assume that's not the case. So I'm going to divide by f prime of x0. And then I'll add x0 to both sides. And basically, this is the way it works. Once you get your x1, you're going to take it and plug it into this side and get an x2. in general, the formula looks like this. It's a recursive formula. That means I'll get my next value based on the previous value. So this is Newton's method. And now what we're going to do is use it in the calculator to solve the problem that I was just doing. So now use the TI-84 to speed things up, I suppose. Or automate. I want to really automate it some. But here's how we do it then. In your Y1, you can't do x sub n's and all that stuff, but you can put an x minus, and then in the fxn, you're going to put, you know what, actually, before I do that, I'm going to rewrite this equation using the language of the stuff that we had. Remember, our function f of x was x cubed plus x plus 1. So that f prime of x would equal 3x squared plus 1. That way, when I'm using Newton's method, x sub n plus 1 will equal x sub n minus, now, I'll have x sub n cubed plus x sub n plus 1. And then on the bottom, I'll have 3x sub n squared plus 1. And now I'll let my calculator do most of the work. Here's what we're going to do in your calculator. Y1 equals x minus, you have to use parentheses, x cubed plus x plus 1, divide 3x squared plus 1. Let's go ahead and put it into the calculator. So I have x minus x cubed, make sure you come down off of there, plus x plus 1, end the parenthesis and begin a new one after you divide, 3x squared plus 1. I'm not interested even in graphing it or anything like that. I just want to get out of this screen. And what I'm going to do, my initial guess was -1. So what we're going to do is take -1, and I'm going to store it into x. Now I want the y1 value of that. So you can go and get the y1 value by going to vars, and then moving over to where it says yvars, and function. That's we had it in the list of functions, so it's already in a good spot. I'll hit enter, and I wanted y1, that's where I put it, and I'll hit enter to bring up y1, and I'll hit enter again. And I see that y1 equals -0.75. Well, this is going to be our second guess. This is going to equal x1. So then what we're going to do is store that as our new x, enter, and then go and get the new y value. So go to yvars, function, y1, enter. And then we keep repeating the process. This now becomes the new x value. I'll store it into x. I'll hit enter. And I'll go vars, yvars, function, y1, enter. Now what I'm looking for, if I want 6 decimal places of accuracy, when I look at the last x versus the new x, I want them to agree in 6 decimal places. Actually, I prefer 7, that way I'm guaranteed 6. So right now if you look, I have 0.68, 0.68. I'm not even really at 2 yet. So let me store this into x again. And you just keep going until you get the accuracy you want. This process actually is pretty fast. Let's go to vars, y1, enter. Now look what I have here. Now I have 0.6823, 0.6823. I've locked down 4 places. So let me store x. I think I might have it this time. This might be the one that does it for me. And let's take a look. Between the last version and this version, I have 1, 2, 3, 4, 5, 6, 7, 8. I'll even say 9 because these will round to a 4. I have 9 decimal places. This is more than enough. Therefore, I have my answer. So, I've shown you how to do the calculator. What I'll have you do on a test is just list for me the x's that you used. And I'll know if you're doing it right because of these formulas, and you'll tell me where you started at. Or actually, I might even tell you where to start at. And then you'll give me the rest of the numbers, and I'll be able to tell if they were right or not. So, and these are all approximations. Nothing's exact here, but let me see how far I can go up. Let's go back and get some of my previous x values. Negative 0.75 was my x1. There it is. So my negative x2, or my x2 was that one. We have 0.6860,465. And then x3 was the next one after that. So 682,3396. Notice I'm doing one more decimal place than what's required. Use as many of these as you have. Usually I have a table of values, and maybe you won't use all of them. Or maybe I'll just have you go through a few iterations or something like that. Let's see, what was the next one? That was the 23396. Then my next one after that was 682,3278. 3278. X5. Right here, it's getting close. I think X5 was the one that did it. Let's see if I'm right about that. Yep, X5 was the one that did it. 682328. So 682328. That's to 6 decimal places. So this is our solution to 6 decimal places. All right, now I want to do another example, but this one is completely devoid of any handwork except for taking the derivatives. Let's use Newton's method. To approximate the intersection point. Actually, I'm going to say the solution to ln x equals x cubed minus 2. Well, what you want to do is, that's not the phrasing you want it. You want to take it all to one side and instead we're going to solve ln x minus x cubed plus 2 equal to 0. So the first thing I want to do is get something of an estimate on where to start as far as a guess. So the first thing I'll do is put y1 equals this stuff. So ln x minus x cubed plus 2, and then I'll just zoom 6 it. Clear this out. Ln x minus x cubed plus 2. And then I'm just going to do a zoom 6. And it looks to me like 1 wouldn't be such a bad estimate. So my guess will be, so a graph that I have here kind of goes like this, around 1. So my guess will be x sub 0 equals 1. Now remember, the formula is x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. What's the f here? Well, that's this stuff. I'm going to use f of x equal to ln x minus x cubed plus 2, so that f prime of x equals 1 over x minus 3x squared. So when I do my xn plus 1, that'll be x sub n minus, and you'll have to put this ln of x minus x cubed plus 2 divided by, parenthesis, in the denominator. You can do this. You can do x to the negative 1 minus 3x squared, like that. So now get rid of this y1. I don't need this y1 anymore. My new y1 will be this. So erase the y1 that you have in here and replace it with this y1. And you could work with y2 if you don't mind. That's fine with me. I think it's unnecessarily complicated. You just replace your xn's by x's. And it will look pretty much like this. Let's go ahead and throw it in exactly the way it looks as I've written it here. So I'm going to change my new y1. Let me clear this out of here. I'm going to get x minus, parenthesis, ln x, finish that parenthesis, minus x cubed plus 2, finish that parenthesis, divide, new parenthesis, x. Here's this little to the negative 1 button, so it'll keep it up there like that. Minus 3x squared. Finish that, and let me get out of this screen. So our initial guess was 1, so I'll do 1 store x, enter. Now what I'm going to do also is keep track of my values. So x, 0, x, 1. I don't know how many of them I'm going to need. I'll just write down, I'll make placeholders for a bunch of them. So x0 was 1. All right, let's throw it in and let's find, we already got it, I've already got it in for x. Now let me go to vars, yvars, function, y1, enter. 1.5 for my x1. All right, now I'm going to plug that back into x. So store x, enter, vars, yvars, function, y1, enter. 1 point, now I want 7 decimal places while I'm doing this. So 3406244. 3406244. And I believe that was 1 point. So right now I don't have nearly enough decimal places of accuracy as of yet. Now I'll store this into X. Enter. Give me the new Y value. Okay, I have basically just 1 decimal place. So I have 3155843. So just 1 decimal place so far. Store it into X. Enter. And then give me vars, yvars, function, y1, enter. I'm getting almost 3 decimal places here. I get 3149791. 3149751. Just make sure that's right. It's a lot for me to remember. 3149791. I don't know what 791. 791. Okay. All right. Well, you can see I'm getting there. Now let me throw this into the next one. Store it into X again. Store into X. Enter. Vars. Yvars. Enter. Y1. Enter. Now look what we have here. I've got 31497. I'm getting there. I'm getting there. We have 5 places right now about. So 3149787. 3149787. And then X6. I bet you I have it on this one. So I'll store this into X. Enter. And let me get my yvars. Gotcha. You can see I have the same exact decimals for the next one. 1.31497787. I only need 6 places. 1, 2, 3, 4, 5, 6. I do not need that 7. So what I would put here, then I would round it to the 6th place, and there you go. There is the estimate for that answer. Now there's the last thing I want to mention is just a couple of concerns that you can have with Newton's method. And to be honest, I never ask them on tests or anything. It's just you should be aware of them because you might encounter them in homework or something like that. One of the things, so what could go wrong? Well, you could be trying to get the zero of a function, but at some point is completely horizontal, like so, and then up, goes up like that. If this is what you're trying to locate, and you choose as x naught or any of your x's something that falls under a horizontal tangent line, the derivative is 0. Then you can't even start Newton's method. Can't even start. So this will break down immediately. Other things that you might have that cause some issues are if you have something like a really, really wide kind of thing going on. I'm not doing it justice here, but this might be like x to the fourth, x minus, I don't know, x naught to the fourth, or whatever. But if you go like to x to the sixth, x to the eighth, x to the 10th, what happens is the graphs start to become more horizontal looking as you increase the powers. Well, this is practically as bad as what I had up there. Although you don't get a horizontal tangent line, you'll get tangent lines that are very close to horizontal. And what will happen is Newton's method will take all day to get an answer. And in fact, you may not get an answer in any reasonable time frame. So in situations like these flatnesses, there are some other cases. Read the book for some other technical details on when things can go wrong. Generally speaking, I would just ask to see that you can show me the steps. Use your calculator to do these things. I'm not expecting you to do these by hand. And most of the time, the answers should be rather quick.